Yes.
So you want us to use a rectangle instead of a trapezoid?
Yes. So we're trying to approximate the true area formed by from 0 to 1 and under the curve here, and we approximate the area here, the sum of S1, S2, S3, S4 by the sum of these rectangle,
I
right?
was just wondering why we use a rectangle instead of a trapezoid.
Yeah, we do step by step, you see. So this is an approximation. It is not a true area, but we are trying to our best to approximate this area. Okay. And let us find and recall this. Okay, the first example. So use rectangles to estimate the area under the parabola y is equal to x squared from 0 to 1, okay, as in the figure here. And if we discretize the interval from 0 to 1 into small sub intervals, here, let me see. Okay, the first one is from 0 to 1 over 4, and then from 1 over 4 to 1 half, and then from 1 half to 3 over 4, and then 1. The first interval from here to here, we call it I1, okay, which is from 0 to 1 over 4. The second interval, I2, I3, and I4 here. Or let us define this. Let us call the first one is I0. Just notation. And therefore, I1 is the interval from 1 over 4 to 1 half. I2 is the interval from 1 half to 3 over 4. And the last interval is from 3 over 4 to 1. So if we approximate this area, then we call the areas of these approximation triangles. So each you see that each rectangle above bless you, has a width one over four, right? The way we discretize the area. And the height of this triangle, look at this. What is the height of the first rectangle here? It's satisfying the equation here, right? Yes, it is 1 over 4 squared, or 1 over 16. The same story. What is the height of the second rectangle here? Yes, 1 over 4 or 1 over 2 squared is the second one here. Okay. And this one, it is this guy square, right? 9 over 16, perfect. Or 3 over 4 squared. And the height of this guy is 1, right? Very good. So the sum of these rectangles will be the width, which is 1 over 4. So the height of them, let us write it down. The first will be 1 over 4 square. The second will be 1 over 2 square. The third triangle will be 3 over 4 square. And the last one will be 1. Okay, therefore, let R4 be the sum of the areas of these approximation rectangles. Then it is clear that R4, it will be the first rectangle, which is the width 1 over 4, times the height of that, which is 1 over 4 squared, right? And the second triangle, which has the same width 1 over 4, and the second one has the height of what is it? Yes. Plus the third one will be 1 over 4 and
3/4 squared.
Thank you. And the last one, it is 1 over 4 times 1 squared, right? Then they are the sums of numbers. You can compute it easily. The final result, it will be 15 over 32. It is approximately 0.46875. This is an approximation of the areas, right, of this curve from 0 to 1, the area under the curve. Okay.
Do we have to like say if it's over or under approximation?
Sorry?
Do you want us to write down if it's an over approximation or under approximation?
Very good.
Like, do you want us to write that down?
Yes. We see that the area of these rectangle is always larger than the true area of this curve, right? Therefore, very good. So we see that their true area of S is less than R4, right? Therefore, let us call it A. Smaller than 0.46 A75. Or if we call it S here, then let us write this here, okay? The similar story, okay? If there's some text here. Why would we do 3/4 to the 4? Oh, there's a mistake there. Oh, I'm sorry. Thank you. I say something and I write something else. Thank you, Michael. This is 3/4 square. Very good. Okay. The same story. If we approximate the area of this guy, by these triangle. The first area we approximated by 0. The second one we approximated by this rectangle. The third one we approximated by this rectangle. The fourth one we approximate by this rectangle. Okay. Similarly, we approximate it. So we see that the lower approximation, which is similar, L4 will be the area of these rectangles. The first one, which has the same width, 1/4, and the height is 0. The second one here, right? It is the width, which is 1/4. Multiply with the height. The height of this guy is this height, right? Which is 1/4 square. And the third rectangle, it will be 1/4 and multiply with the height. And what is the height of this guy, Gary? Perfect. It is 1/4, or let us say 1/2 square. Okay. And the last rectangle is 1/4 multiplied with this height. This is 3/4, which is 3/4 square, right? The same story. But then we do this computation. We got that the area of this guy is 7/32, which is approximately 0.21875. This is another way to approximate the area of the problems, right? And we see that the sum of these rectangles is always smaller than the real area. Okay, we call it the lower area. And we see that L4 is smaller than the true area. Okay? And if we create a finer mesh, if this rectangle has a smaller width, right, then it is easy to see that the area of these approximation, the lower approximation and upper approximation, will come closer to the real area of S. You see it? Right? We reduce the width of each of rectangle here. It will reduce the gap here. So that is the idea of the approximation. Okay. So similarly, in general, if we create a finer mesh, discretization if we create a finer the lower and upper approximation using an rectangle. And we have a table like this. If we have n rectangle, and we call it lower approximation Ln and upper approximation Rn. When n is equal to 10, we have the result of lower approximation is 0.28500000, and the upper approximation is 0.38500000. And you can do it. Go home and do it. It would take a lot more time if we discretize it into 20 rectangles. Then it get the result 0.30875000, and the upper approximation is 0.35875000. And you keep doing that. And this is the result of the area when we approximate the real areas by 100 rectangles. And the lower bound, the lower area is 0.3283500. And the upper one will be 0.3383500. And if you do it more with a 1000 rectangle, then the lower area would be 0.3328335 and 0.3338335. You see that according to this table, if we approximate the real areas by more rectangles, the lower and upper areas will come close to each other, right? And finally, we conclude that the area is approximately 0.3333335. Okay. This is an example that leads us to a definition of the area of any curve formed by any curve, that the area A of the region S that lies under the graph of the continuous function f of x is the limit of the sum of the areas of first one is the area will be the limit of Rn when n approaches infinity, which is the limit when n approaches infinity of f of x1 multiply delta x plus f of x2 multiply delta x until f of xn delta x here, or it is the limit when n approaches infinity of Ln. In more details, it is f of x0 multiplied with delta x plus f of x1 multiplied delta x plus f of xn minus 1 delta x here, where we discretize the interval from A to B into n intervals. And this, we call it x0. This is x1. This is x2. It continues until this guy, we call it xn minus 1. And the last one is xn. Right. This is how we discretize the distance from A to B. And each of them here, each of the intervals have the same width. And we call it delta x here, where delta x here is the difference between B and A divided by n, the numbers of intervals. Okay. From this relation, because delta x is a constant, right? Therefore, we can write x1 is x0 plus delta x, and x0 is A, right? From this, we can compute x2 from x0, from x1, right? And we know that x1 is x0 plus delta x, right? So this implies that x2, what is it? If we write it in terms of x0, it would be? Yes, times 2 here, right? Very good. Yeah, or x0, we can write it, yes, the same things. A plus 2 delta x. Right? Very good. So it means that if we're given a and b and the numbers of intervals, we can easily compute x0, x1 until xn. So it means, and we are given the function f, then we can evaluate f of x0, f of x1, etc. here, right? But sometimes we don't want to write this long. We want to make things simpler, shorter. It makes us makes our life easier, and we use the sigma notation. We write it. The sum when I is equal to m until n of f of xi multiplied delta x. Let us write from 1. It means I will run from 1 to n. And we can write it clearly as f of x1 multiplied delta x plus f of x2 multiplied delta x, right? Plus f of x3 delta x, etc. until f of xn delta x. Shorter to write it, okay? We call it, this is the sigma notation. So is the idea clear now? Yeah, we approximate the area formed by any curve by this approximation. Very good. And another types of problems. Let us call it the distance. Problem. For these problems, we are given the velocity field. We need to find the distance. Okay? And remember, the distance is the velocity multiplied time, right? Or if we write the velocity in terms of distance and time, right, we can write it this way. Okay. So let us consider this example. Suppose the odometer on our car is broken. And we want to estimate the distance driven over a 30-second time interval. We take speedometer Okay, take speedometer, readings every 5 seconds and record them in the following table. Now we're given the table like this. This is times, this is velocity. Okay. And the initial times is 0, 5, 10, 15, 20, 25, and 30. The corresponding velocity is 17. This is mile per hour. This is 21, 24, 29, 32, 31, and 28. Okay? Now when you go home, think about these problems, and tomorrow we will continue. And class dismissed. For people you want to do a makeup test, please wait. See you, everybody. Yes.
Could you scroll up in the notes?
Sure.
I just wanted to see something.
See?
Like at the top, there's whenever we were doing the interval, those. So that first, I don't want to touch it.
Yeah, sure.
A little further down. Like whenever it gets to the instant pause.
Oh yeah.
Can I touch it? Are you
Sure,
gonna
sure.
be?
Sure. I'll be ready. We are going to another building. Yeah.
I was just curious how far off from the, like from a lower approximation and an upper approximation, like the average of them, how far off it would be from the most accurate one. I was just curious.
Yeah, yeah. Interesting. I haven't. No. Sorry.
Thanks, Mr. Byrne.
You're welcome. Have a good one.
I'm sorry I haven't been here.
It's okay.
I've been so busy.
Yeah. How was the trip?
It was fun. We got fit at SECs. So.